Good afternoon. The next speaker is Daniel Farkas. I have known Daniel for some time. In fact, we met at asbestos. Oh, I'm sorry, Tim. I do apologize. It's yes, Dr. Daniel Farkas. Yes. So if he can, please. He has put his introduction already. He has even written a book on calculations. So
okay,
I'm so
I just
that he's
put the presentation. You should be able to see the slideshow.
Yes, actually, I was just mentioning about your book that you have written too. So it is a calculation book that is very useful for the CIH exam. Thank you.
Okay.
Right, take it away, Dr. Farkas.
Okay,
Yeah.
thank you. Yes, I'm Dr. Daniel Farkas. Please call me Daniel. I encourage my students to call me Daniel. To tell you a little bit about myself, I also have English as a second language. When I started learning for the CIH, there was actually no book on the CIH exam equations, and it took me about a year just to gather all the information about each equation. And after I passed, I said, I want other people to have this information. So I put it as a book, so that was the first book I wrote on CIH. It was the math equations. And that was very successful. And then I had a second book, which was basically the technological background of the CIH exam, where are all the technical questions. Let me see if I can go to the next slide. The slides are kind of moving kind of slow. So let's see. And of course, if you go to the to my LinkedIn page, you are going to see all my work history. Let me see. For some reason, I don't think the slide is moving forward. Let me see. Okay. All right, I think it's starting to move now. Yeah, so the yellow book, it's basically the CIH exam equations that are simply explained with examples, because you'll find them like parts of them in other books, but they're very, very complicated, and they don't give well explanations, and that's what actually was the catalyst of and determined me to write this book. And the second one, it's the CIH exam equation practice. Basically, it's as I said before, it's just the technical literature where you learn about concepts like sound and noise and light, what is light, and if you go and you ask somebody, like a physics professor, what is light, they'll give you a definition. But if you ask somebody like a Nobel Prize winner, for physics, what is light? I asked Dr. Barry Barish, who got the Nobel Prize based on, he actually discovered, he proved the existence of gravitational waves. And he said, like, I don't know what is light. It's very complicated, So it's kind of the same thing. Is like you have to look at this science, not that you understand everything, but keep a curious mind, because you'll find some scientific um, curiosities among the CIH concepts. I also have a CIH exam essential practice. It's an audio book, and I only got 25 free audio book free codes, so I can only give 25 of them. So this is a unique code that will give you the right on Audible to get my book. My book is 6 hours and 6 minutes, and it's narrated by me. And if you go on LinkedIn and you ask me for the code, you can send me a message and say, hey, I'm one of the students taking the class. I would like a free audiobook code for the CIH exam. The first 25, I'll give them free audiobook codes, because this is how many I got from the producer. Again, if you go on LinkedIn, look up Dr. Daniel Farka, CIH, CSP, CHMM, write me a message. And as soon as you write, because we all have access to the phones, I'll reply and I'll give you the unique unique code. So I cannot give it publicly. So let's also there I did 3 videos that are now on Vimeo. It's the ventilation CIH exam, the noise CIH exam, and the radiation CIH exam. I'm working on the last video, but these videos are there and they are available for you to watch. And you're actually going to get a preview of these videos in today's presentation. And let's see. Okay. Let me start with today's presentation. And after this, I know everybody wants a 10 minutes break. We're getting close to 7. I'll give you the 10 minutes break after this slide. This is the CIH exam equation sheet. It's and it's called explained. You'll see you'll have in the ventilation chapter is 29 equations that you need to know by heart. It's usually better to know them by heart, because although you have access, you don't want to lose the time and go and look up an equation during the exam. It's better if you know it by heart, and I'll teach you some tricks to remember them. The noise chapter is 20 equations. The general science, statistics, and standards is 35 equation. The heat stress is 5 equation. The radiation is 28 equations, and the hood airflow equations are 9. And this is basically from the board's website. This is the source right there. You can go and download the CIH equation sheet there. And also it's important to see their statement. It says this is a list of equations that is offered as assistance in taking the examination. So it's not the American Board of Industrial Hygiene anymore. It changed. And there is no assurance given that this list is complete. So you have to understand how to use the equations, because even if you have them there in front of you, you may need to use other equations beside this equation that you see over there. And there was no attempt to standardize this equation, and you'll see 2 types of equation. One is metric, so basically for people that start learning science in Europe, you're gonna recognize meters and seconds and kilograms. And the other one, is the American or the English system in inch and pounds, and you should be able to switch from one another. I usually use the metric one just to make sure that I got the good result. And let's see. So let's do 2 more slides before 7 o'clock. Let's remember, we're gonna start the ventilation chapter, but let's remember some basic ventilation ideas. This is the basic components of a local exhaust ventilation is the hood, basically, which is the entry point, the duct, which conducts or the gas travel, and basically everything is a fluid. A liquid is a fluid, a gas is a fluid. And then you have the air cleaner, which removes the contaminants, the fan or the energy source that pulls the air through the hood and it push it through the exhaust, which is the exit point. And also remember the local exhaust ventilation removes contaminated air from the worker's breathing zone, and the geometry or the shape of the hood basically drastically affects the hood efficiency. And we'll see that in the end. Different type of hoods, you have different type of efficiencies. So how many type of ventilation methods are used in the occupational environment? There's two. It's the local exhaust ventilation, which is an engineering control that minimizes the worker's exposure to airborne contaminants like dust, mist, smoke, vapors, or gas by simply vacuum the airborne pollutants out of the worker's breathing area. So these are like local area, and you have to think about the breathing area of the contaminants. As closer you get this local exhaust ventilation to the worker's breathing area, the better it is. Or if you can catch it basically at the source where this contaminant is produced. And also there is the dilution ventilation, and it ventilates entire workplace and exhausts large amounts of contaminated air while bringing in clean air to reduce or dilute the contaminants concentration. And this is the part that employers don't like because it's very expensive. You have to take a lot of air, and if it's like cold outside, you have to air conditioning to cool it down, or if it's really cold outside, you have to heat it up before you bring it in the factory, for example, or in the working place, and you have to clean it, which means you have to change the filter a bunch of times, and that's the most expensive one. In this situation, dilution ventilation is used for contaminants with also extremely low toxicity and minimal and uniform contaminant generation when sources are between the employee and the air return. Okay, let's see. Let's do one more slide.
I mean, if I may, actually, if I may interject for a second about the dilution ventilation.
Okay.
Right now, actually, a couple of months ago, because of the COVID, it has been very highly discussed because on the buildings, they are trying to put MERV rating filters, at least MERV rating 13, 8 to 13, for especially because of COVID. So normally in commercial buildings, you have a charcoal filter and then you have another filter for dilution ventilation. Thank you.
No, thank you, Sarat. And I appreciate, I was just talking about like how much I'm amazed about your career, you know, you're a CIH and your dedicated.
I mean, just I have been with the area for so long, you know, I'm an old timer. Not that I'm smart or anything. I'm just encountered so many things in the past. That's it, you know.
Yeah, about 30 years in the military, that's a lot. So so let's do this. It's 7. Let's take a 10 minutes break, and I'll see you back at 7:10, if that's okay.
Did thank you, Dr. Farkas. Did anyone
Yeah, please
join?
call me Daniel. Yeah.
Daniel, did someone join who didn't get to introduce themselves? I know somebody had trouble with the link. All right. I guess they didn't make it on. All right, let's take our break. We'll see you in 10.
Hey Tim, about the recording. So record to this computer. I'm going to stop it then.
If you can pause it, that you know, so people don't have to sit through when they watch the recording, they don't have to, you know, sit through 10 minutes of break time. We just
Uh,
have to remember to unpause it.
Actually, I'm in stop recording. Okay, I stop recording. Okay.
Can you restart it later?
Hopefully I can. If you can stay with me for this first session, please.
Yeah.
Sorry about this.
I would
No.
keep it just in case, you know.
Okay. Yeah, we don't want to mess it up.
If it's not broken, don't fix it.
Yeah, there you go. All right, I'm gonna go take a quick break. We'll see you
No, me too.
in a
Thanks.
Okay, so welcome back. Now let's talk about, I think everybody's back in, right?
Hi guys, welcome back. I opened the recording again. I hope it's correct. So
All right. So I think everyone it's back online. Let's talk about the Reynolds number. And this is not Ryan Reynolds from the Mint commercials, right? The Reynolds number describes the flow turbulence and characteristics of air and other fluids. So there are three types of flow based on the Reynolds number. If it's less than 2,300, it's laminar. So basically, looks like when the flow it's kind of frozen. It's still, and I'm sure you've seen a lot of images there. It looks like the flow is frozen, but it's not. Between 2,300 and 4,000, it's unstable, and above 4,000, it's turbulent, and you can see a turbulent flow. And these are some basic concepts before we go and we do the math. We go again here. Let's see. Another thing about fluids, they have a normal and a standard temperature or pressure. So every time you go and you're gonna solve a problem, think about this, like what is the standard temperature and pressure there, or what is the normal temperature and pressure? The standard temperature and pressure, it's 32 Fahrenheit or 0 Celsius degrees. So this is freezing temperature. And 14.7 psi, right? Per pounds per square inch, or 1 atmosphere, or 760 millimeters mercury column. The normal temperature and pressure, it's 68 Fahrenheit, which is a big difference from 32 Fahrenheit or 20 Celsius degree. So this is the most common temperature that you'll find in the factories. And again, it's 14.7 psi or 1 atmosphere or 760 millimeters of mercury column. And there is also ideal gas. For the ideal gas at standard temperature and pressure, the molar volume is 22.4 liters. That's why you have to watch that in equation, because a lot of people, they know how to solve the equation correctly, but they put the wrong information or the wrong values in the formula. And normal temperature and pressure, the molar volume, it's actually 24.04 liters. This note is actually the most important in this slide. Also, this is another problem when you're doing the sampling, and I've seen this a lot of time, during the CIH exam. It says if an IH is sampling the exhaust stream pipe of the emission stack and the sampling velocity is less than the exhaust stream velocity, what kind of error might the results have? So the results will have an oversampling error because a large particle, due to inertia, will contribute, as you can see in the picture, will contribute into the probe, while small particles will follow the gas stream and will not be sampled. The result will show a contaminant concentration that exceeds the actual concentration. So that's basically why you have to match, the sampling flow with the particle flow that you are sampling from. So usually it might be a pipe or it might be a air draft somewhere. So that's important. Note, if the sampling velocity is higher than the exhaust stream of the emission, we will have undersampling. In undersampling, the smaller particle follows the gas stream and will be sampled in higher numbers than the large particles. The results will show a contaminant concentration lower than the actual concentration. So the IH must take uniform or isokinetic sampling. So basically this is what I want you to remember. If you sample for smaller particles, that will be basically show concentrations in lower. If it's bigger, that exceeds the larger concentrations. Let's do a simple problem before we go to more complicated one. How can we calculate dangerous air contamination in confined spaces? If isopropyl alcohol of high purity spills inside a confined space, and we know it has a vapor pressure of 44 millimeter mercury column at normal temperature and pressure, will the isopropyl alcohol equilibrium concentration in the air exceed the 2000 parts per million, which is the immediately dangerous to life and health? So in this situation, we know the atmospheric pressure equals 760 millimeters of mercury column, right? So the vapor pressure of isopropyl alcohol, it's 44 divided by 760 parts per million. Then we multiply that, of course, with 10 to the power 6 because it's millions. That will result in approximately 57,895 parts per million, which is way above the permissible exposure, not permissible exposure level, but above the immediately dangerous to life and health. And I'm gonna go to the ventilation chapter. And as we seen, there's a lot of equations over here. Because today's 2-hour presentation, I'm just gonna go through the several, but the most important one. As you can see, the one in brackets, it's actually the metric version of the equations before them. So that's the English it's called the English world equation. But once you learn one, you just have to see there's a different constant they use, and it's basically the same equation. So once you learn one, you learn this all of them. So you see in the second row, it's 4005, and then it's 1.29. It's going to be used again as 4005 and 1.29 because you have metrics, and then you have the English system. And let's go with the first equation. This is actually the easiest equation, but just to make sure, we have a chat here. And before we go,
Yeah, it says imperial versus metric.
imperial, okay, imperial and metrics.
Yeah,
We call them English, but we will use imperial.
yeah.
Okay. And I remember there was a story about how they come with the foot. They use the length of a king foot or something like that, right, Richard? They didn't have a standard. They said, use my foot as a standard. And that's how they got the foot. But I want to do something. I kind of want to do a statistic just to make sure the chat is working because I'm going to ask questions and along the way. So just a curiosity, if you want to do it, you can write in the chat right now, which country are you from, or, wherever you were born. So for example, I was born in Romania. I'm just gonna put Romania, I'm just curious to see how many others have, English as a second language, because I was deterred at the beginning. I thought like, oh, I'm never going to pass this exam. So we have India, US, Venezuela, okay, Qatar. Was born in Washington, D.C. That's great. I live in Washington, D.C. Chile, Cameroon. Perfect. Yeah, so I'll tell you Uzbekistan, yes. I'll tell you even if you have English as a second language, it doesn't mean you're not gonna pass the exam. You might pass the exam, So don't worry about it. It's they want to take the best. It doesn't matter where you're from. Okay, so let's go to the first Peru. Okay. And let me know if you can hear the sound.
The first equation is the volumetric flow rate in a duct.
Can you hear the
This
sound?
equation correlates the volumetric flow rate Q in a duct to the
Oh,
cross-sectional area of the duct A and the duct velocity V of the air or gas flowing through it. The equation is Q equals V times A, where Q is volumetric flow rate in cubic feet per minute or cubic meters per second. A is the cross-sectional area of the duct, and it's measured in square feet or square meters. V is the duct velocity and is measured in feet per minute or meters per second. There are two common types of ducts, rectangular and round ducts. But it's also important to visualize these processes in our minds. The volumetric flow rate in a duct can be visualized as the total volume of air or gas moving through an area per unit of time, which can be minute or second, as you can see in the animation. Round ducts are usually more efficient than the rectangular ducts because they are less airflow resistant. For example, what is the flow of an 8-inch diameter duct with 100 feet per minute duct velocity? The first step is to identify the variables. We have 100 feet per minute, which is velocity, and an 8-inch diameter value that we can use to calculate the duct area. Since 1 foot equals 12 inches, 8 inches divided by 12 equals 0.666 and so on feet, which will round up to 0.667 feet. But we know that the cross-sectional area of the duct or circle area equals P times radius square, or P times diameter square divided by 4. That's because the diameter is twice the radius. And now, using the flow formula, we can calculate the flow rate from velocity and area. So the duct area equals 3.14, which is P, times 0.667 feet squared, because it's the diameter squared, divided by 4. And the result is 0.349 square feet. In the end, the flow is 100 feet per minute times 0.349 square feet, which results in 34.9 cubic feet per minute.
all right.
So we have to learn to do the calculation really fast on our calculator. And for this example, the diameter is 8 divided by 12, which equals 0.667 feet. We square the answer and divide by 4 and then multiply with 3.14, which is P, to find out the duct area. And then multiply with 100 feet per minute to find out the flow value, which is approximately 34.9 cubic feet per minute. Save time during the exam by learning to be fast on your calculator.
Okay, so I think this is
For
the
this next example,
another one.
we have to calculate the flow of a 0.5 by 0.6 meters duct. This is a rectangular duct with a 1 meter per second duct velocity. First, let's identify the variables. We have 1 meter per second, which is velocity, and 0.5 by 0.6 measurements of the duct sides. In this case, it's easy and fast to calculate the area. The area is 0.5 times 0.6, which equals 0.3 squared meters. And then we just multiply the result with 1 meter per second to find the flow value, which is 0.3 cubic meters per second.
Okay, so I think it's the recording. It's over. This is one of the rare occasions where you get to interrupt yourself, you know. But I think this is the best way you can show the students, you know, how to do stuff on. Thank you, Tim. I appreciate it. You get to show, you know, how to actually do the calculations on the calculator, because otherwise it would be impossible for me to hold the calculator right here and push the buttons. So this was an easy one. Prepare, it's gonna get more difficult and difficult as we go by. I'll check the chat. Do you have? You can
No, there's
unmute
no
yourself.
questions in the chat, Daniel. Actually, one thing that I wanted to mention is this is a great example. The pictures are really fantastic. I mean, you did a great job. But the main thing that you got to, one of the main things that you got to be careful is the units, you know. So in the exam, sometimes you may not be able to convert inches into feet, and people make that mistake. And if you don't convert it, you will see the result in the answers. Okay, so out of the 4 answers, the wrong answer will be there with the unit being wrong. So a lot of people, what happens is the units is the main thing that they get flawed in, you know, because you're in such a hurry to complete it too, you know.
Yes, yes, of
Thanks.
course. Yeah, I mean, you have to adapt. If you have meters, you know, use meters, right? The second example was meters. The first example was feet. So you have to adapt your mind, you know, to go from the imperial system to the metric system. So the good part about the metric system, it's 10. You know, it's like everything is tens. You know, but with the imperial system, if you have feet, yards, ounces, you know, and then you have to get your mind into that one. So that's the biggest difference. So Chris, I see you. I was there in your area today. I work somewhere nearby. I saw there were a lot of police cars in the Teamster area.
Yeah, Biden made a visit at the building today. Yeah,
Okay. So
yeah.
did you get to see the president?
I work from home today.
Ah,
But quick question.
yes.
As far as the constants for the math, when you're doing those conversions, should we be expected to kind of know that off the cusp, or does the exam kind of give those throughout, or what? What's
So
your thoughts on that?
usually that's a good question. That's usually if they give you the question in meters, they expect the answer in meters. You know, I mean, they try to see if you know how to use the right formula. So most of the people that took the exam and, you know, they have the experience, they said, you know, they never try to trick us. with like petty things. They try to trick to see if you actually have the knowledge and what kind of formula you should use. So concentrate on the formulas more to understand them, not necessarily that they're gonna trick me not to, they're gonna give me everything in meters and then they're gonna get the answer in feet, you know. But it's good to expect the unexpected. So but it will be like 90% of the case. If I would take the CIH exam again, will be just to learn the formulas, to have them in my head. So I hope that answers your question. So now let's go to a more difficult question from the ventilation. I hope you're gonna enjoy this one.
There are three pressures working inside any duct: static, dynamic, which is velocity, and total. The static pressure is the pressure of air pushing against the walls of the duct sections. The velocity pressure, it's represented by the velocity and weight of air. And the total pressure, as the formula shows, is velocity pressure plus static pressure. Total pressure, annotated with T and P, is also known as the head or energy in the ventilation flow stream and measured in inches of water column. You'll see the letters IN as in inch and WC for water column. Vp is the velocity pressure within a duct, not to be confused with velocity, which is V, and is measured in inches of water column and not in feet per minute as we have for velocity. Sp is the static pressure within a duct and is mainly manifested as pressure on the duct walls, and it's also measured in inches of water column. This equation is known as conservation of energy, assuming no friction losses. It states that total pressure, which represents total energy, is the sum of velocity pressure, which is movement pressure and always positive, and static pressure, which represents the pressure of air exerted in all directions. Again, static pressure, or SP, is pushing inside the duct walls, while velocity pressure, or VP, is moving the air in the direction of the flow because of the pressure differentials. Air moves from high pressure to low pressure. Velocity pressure is parallel to the direction of flow and can only be measured as the differential between total pressure and static pressure. Static pressure is expressed equally in all directions and is measured perpendicular to the direction of flow. Static pressure is the pressure a fluid would exert on its surroundings if it was not moving. Dynamic pressure, also known as velocity pressure, is the pressure caused by the velocity or movement of the fluid. For example, what is the total pressure in a duct pre-fan if static pressure is minus 2.25 inch water column and velocity pressure is 1.5 inch water column? Remember that the velocity pressure is only exerted in the direction of airflow and is always positive. Pre-fan, the total pressure is always negative. That means that the air flows into the duct system. So, for our example, we have total pressure, which equals velocity pressure plus static pressure, which equals 1.5 inches of water column plus minus 2.25 inches water column, which results in minus 0.75 inches of water column.
All right. So basically, you got the main idea. Pre-fan, the static pressure is always minus. Post-fan, because it's pushing and it's pushing the air forward in the pipe, it's also pushing in the walls. So it's positive. That was the main idea. And now we're getting to higher and higher concepts. Another thing, the good thing, one of the great thing is like I signed a waiver, and I send it to Tim. You can watch this as many times as you want. So even if you have like questions later, you can come and re-see this whole presentation. And if you have even after that questions, just write to me on LinkedIn. And I want to thank to Tim because Tim put everything together, and I know how difficult it is to organize this whole thing. We couldn't have done it without the help of Tim. Thank you, Tim. Let's go to another equation.
This equation is used to calculate the hood static pressure required to overcome as air or gas enters a hood. Hood static pressure is a measurement of the drag created on the airflow through the ventilation system. The amount of static pressure that the fan must overcome depends on the pressure velocity in the ductwork. The formula is SPH, which is the hood static pressure and is measured in inches of water column, VPD, which is the velocity pressure within the duct and is measured in inches of water column, and FH, which is the hood entry loss factor or friction loss coefficient and is dimensionless, which means lacking any units. As you can see in the animation, the gas or air molecules exhibit a resistance to the airflow within the hood. There are some other variables that are not pictured in this animation that will slow down the airflow, like a grill or a filter. For example, calculate the hood static pressure if the hood duct velocity pressure is 0.6 inches of water column and the hood entry loss factor is 0.45. And we are going to use the calculator for this calculation. First we have minus, open parenthesis again, 0.45 plus 1, close parenthesis, times 0.6, close parenthesis, which equals 0.87 inches water column. In this example, minus 0.87 inches water column is necessary to accelerate air to hood opening to duct velocity and overcome any associated turbulence losses.
Okay, so when you hear me going open parenthesis again, that's not a stator. You have to do that, and you have to learn how to do the calculations just because the calculator's mind requires that. So there's going to be some tricks where you're going to see 3 parentheses. Please pay attention to that because it's going to help you a lot of time during the exam. Now let's go to another equation. This is a little bit more complicated.
This equation is used to determine the volumetric flow rate of the airflow into the duct through the hood with just the hood static pressure, if the hood entry coefficient is known. In this formula we have Q, which is the volumetric flow rate of duct and is measured in cubic feet per minute. 4005 is a constant and conversion factor based on the air flowing at standard temperature and pressure. The Hood entry coefficient is dimensionless. The value of the Hood static pressure is measured in inches of water column. The air correction density factor equals 1 at standard temperature and pressure. And A is the cross-sectional area of the duct in square feet. Now let's do an example. Calculate the volumetric flow rate of a 6-inch diameter duct which has an area of 0.196 square feet from a hood if the hood static pressure measurement is 2 inches water column. Also, the hood entry coefficient is 0.98 because it's bell-shaped with a density factor of 1. So the calculations are Q equals 4005 times 0.98 times square root of 2 divided by 1 times 0.196, which equals 1088 cubic feet per minute.
And that's of course approximately because this is how we get the values. We never get them exactly, exact match. So make sure that you know how to approximate, above 5. So above 0.5 is like you round up to the highest number, below 0.5 to you just take it one number down. So I'm sure everybody knows that.
Um,
Okay,
Daniel,
go
I
ahead.
do have a question about the calculators. What models are accepted for the exam?
So there are several models. I have one here, but the one that you've seen in the presentation, it's Texas Instruments. But I understand you have to look this up. They're not going to allow calculators anymore because something happened and they decided not to allow students with calculators. If you're taking, I think, this year, you can still have a calculator and you go on or the board and you download the manual, the CIH exam taker manual, and it says exactly what kind of calculators you can take. When we're gonna have the image again, I'm gonna stop the image and I'll tell you exactly. I think it's the Texas Instrument S something. So we'll see in a second. All right, let's go to the next equation. Isn't PowerPoint great? You can do anything in it these days. It's amazing. Okay, so let's go to a more complicated one. I did do this equation with somebody online, and he said, like doing this equation and calculating gave me a headache. And I said, okay, this is gonna be a small headache. What's coming next is gonna be bigger. So let's do this one first.
This equation calculates the time needed for the dilution ventilation to dilute the contaminant in a room to a lower concentration, but only when there is no more contaminant generation. If you look at the picture on this slide, you may ask yourself when is safe for the scientist to enter the room after a bottle containing contaminant has been spilled on the floor. Remember, this is a one-time event and there is no continuous generation of the contaminant. So the animation will only run once. To calculate the time needed for the dilution ventilation to dilute the contaminant in the room, we need to know the following values. The difference between the final time and the initial time will be in minutes, and this will tell how much the scientist needs to wait until the room is safe for re-entry. Then you have the natural logarithm, which value is 2.7182818. Then the volume of the enclosure, which can be calculated based on room width, length, and height. The initial concentration of gas or vapor in parts per million, the final concentration or the desired concentration of gas or vapor in parts per million. The final concentration is the concentration that is safe for re-entry. And the effective rate of ventilation in cubic feet per minute. For example, benzene spills in a room that measures 40 by 50 by 12 feet, which equals 24,000 cubic feet. An initial concentration of benzene is measured at 50 parts per million, and the benzene use is stopped, so no more benzene vapors are released. With an effective rate of ventilation of 4,000 cubic feet per minute of dilution air. How long it takes to reach a permissible exposure level of 1 parts per million? So the answer is the difference between the final time and the initial time equals, and if you do it this way, it will save you time during the CIH exam, parentheses, minus 24,000 divided by 4,000, close parentheses, times natural logarithm, parentheses, 1 divided by 50, close parentheses. And the answer is 23.47 minutes. Those 0.47 are not seconds, they are percentage of a minute.
So that's very important because you might get an answer where it says 23.47, 23 minutes and 47 seconds, and then you'll have an answer where it says 23 minutes and 30 seconds. Which one is the correct one? The second choice, right? So they might not trick you like that, but you might give involuntarily the wrong answer. And I understand they're experimenting with little boxes where you go and introduce the value by yourself. So that's going to be something new. Let's go to the next one. You're going to like this one more.
Just like the previous equation, this formula is a dilution ventilation formula, but with continuous contaminant generation in a room. The animation on the right shows an ongoing event. There is a continuous source of the contaminant. Again, we have the natural logarithm, which is 2.7182818. The volume of the room or the enclosure in cubic feet, the initial and the final concentration of gas or vapor as percentage or parts per million, the rate of generation of contaminant, which was not in the previous equation, in cubic feet, the effective rate of ventilation in cubic feet per minute, and the initial and the final time in minutes. For example, benzene evaporates at a rate of 4 cubic feet per minute in a room that measures 40 feet by 50 feet by 12 feet, which is 24,000 cubic feet. If an initial concentration measured is 50 parts per million, what will the concentration be after 45 minutes of 4,000 cubic feet per minute of dilution air. The mathematical calculation on this equation are a little bit complicated. But after we plug in the values in the equation, we have to solve this natural logarithm equation, and we get rid of the logarithm by raising both sides of the equation as an exponent to the natural exponential function e. This will cancel out the natural logarithm that we had in the left side of the equation, and this will make the calculation much easier. So we'll have e at the power double parentheses minus 4,000 divided by 24,000 close parentheses times open parentheses 45 minus 0 close parentheses again, which will result in 0.000553084. Then to find out the final concentration, we'll multiply this number times open parentheses 4 minus 4,000 times 0.000050, which is the initial concentration measured at 50 parts per million. And the result is approximately 0.002101721. Now we'll take the 4 from the left side of the equation and move it to the right side of the equation. In the end, the final concentration is approximately 1,000 parts per million, which is twice the immediately dangerous to life and health limit.
Okay, so basically, if you learn to do the equation this way, it will save you a lot of time. Anyone can do this equation if you go and you plug in the values, but you have to learn to do it fast, because I think I calculated with a good friend of mine who is also CIH, and we figure out you have about like 1.4 minutes per question. So for each question, you have to answer within 1.4 minutes. And we kind of figure out like you have to do, to plug in the numbers and do the calculation really fast and move on. And another strategy, and everybody uses this, if you don't know the answer, just keep going, answer whatever you know, and then come back and try to answer what you don't know. So usually math gets left behind, because it's like, oh, I'm gonna do the math part after I answer everything I know. Everybody's good, doing okay so far? Yes, that's good. And also we are
Fine,
very
thanks.
lucky. Oh, go ahead.
We are fine, thanks.
Okay, we are very lucky because I understand, people that took the exam, 40 years ago, the exam was like 2 days, and they had to go through all these equations 2 days, and after they're done, they don't know if they pass or not. They had to wait for to get the letter. But we are the generation that is gonna get the response right away. Like the second that you're done, you're gonna see a screen where it says that you pass or not. So, all right, let's go to the next one.
When airborne contaminants start being released with a known constant rate of generation in a ventilated room, the final concentration of gas or vapor is time dependent. In this equation, we have the final concentration of gas or vapor in parts per million, the constant rate of generation of contaminant in cubic feet per minute. Notice that the rate of generation is in cubic feet per minute and not in pins per minute like in equation 20. The natural logarithm, the amount of time in minutes, the effective room ventilation rate in cubic feet per minute, and the room volume in cubic feet. For example, a room measures 40 by 40 by 10 feet, which is 16,000 cubic feet, and has a ventilation rate of 4,000 cubic feet per minute. Benzene evaporates from an open bottle left on a laboratory table at a rate of 0.1 cubic feet per minute. What is the final concentration of benzene after 15 minutes? So after we plug in the numbers in the formula, we have parentheses 0.1 times parentheses 1 minus E at the power another parentheses minus parentheses 4,000 times 15 close parentheses divided by 16,000 close parentheses, close parentheses, close parentheses, and close parentheses again, divided by 4,000. And then we multiply our answer with 1 million because we want to know parts per million, and equals 24.41 parts per million.
All right, so now let's go to the noise chapter. I hope you enjoyed the animations from the ventilation chapter. Let me know if you need to take a break or not. Do you need to take a break now? I'm just curious. Let's see what the chat says. Yes, you need a break? Okay, we can take a break. Okay, let's take a 10-minute break. I don't know, let's just 10 minutes break, okay? I'll see you back in 10 minutes.
Hey, Sarat.
Yes, I stopped recording, Tim.
Yeah, there's a pause on button for the recording.
Oh,
Apparently,
there's a pause button. Okay, sorry.
at least I saw one.
Daniel, there is a question on the chat for you. Are these videos on your Vimeo, VMEO?
Yes, yes, I'll talk about it. You know, actually, let me see if I can. Thank you for asking, Sarat.
Oh, you're welcome. That's what I'm here for. So
Yes, yeah, here there. All right, I'll just put them up here so everybody can see them. Basically, you can go on Vimeo and watch them. You know, it's I'll talk about them when the students are coming back. So
okay, thanks.
all right, I'll go check on the little ones to see what they're doing.
So we are going to start at about 8:05.
8:05. Okay.
Okay.
Oh.
Is that okay?
Hmm?
Okay, good. Okay.
Okay.
fine.
Great. Thanks again.
Yeah. Hmm? Okay, I'm going to start the recording, okay? Right on the dot, Daniel. Right on the dot, 8:05.
Perfect.
Hi. Daniel, you're muted.
I'm muted?
Okay, now you're fine. Now you're
Okay,
fine.
all right. That's good. So yes, Sarat asked me a question. What can we see the videos for all these formulas? And I basically I was very lucky because I had a great colleague that helped us, a CIH like us. His name is Kent Candy, and probably it was kind of weird in the beginning because I asked him, hey, can you review some IH industrial hygiene animations, you know, and it's like an article or no. It's IH animations. So thanks again, to Kent Candy, and you'll see his name over there for the peer reviews of the slides and the animations. He did a lot of work, and his work is greatly appreciated. But the main idea is that these videos are available on Vimeo. You go on vimeo.com, you put my name, Daniel Farkas, or CIH exam videos, and you'll find them. And this is the page where you'll see them. There's 3 videos right now: the ventilation, the noise, and radiation. And now we're working on the 4th video. These are available. You can download them. You can get them for like a year or lifetime. So there are 2 options over there. But um, I couldn't done it without Kent Candy's CIH help. So let's go back to noise. And there was a good definition of noise. And this is one of the things that actually made me think like industrial hygiene has a good point. It's like, noise, it was defined as, unwanted sound. And I said, when a neighbor is noisy, yes, that's noise because it's unwanted sounds. You want some sounds that are not noise, but this one, and we'll start. I'm sure you already know the easy ones. We'll start with something more complicated. If not, you can go see the videos from the beginning, and it starts again really easy, and it gets gradually complicated. So let's listen to the noise one.
This is the time equivalent sound pressure level, which quantifies the average sound pressure level from a variety of sources over fluctuating durations. Time equivalent sound pressure level is often used in environmental noise assessments, workplace noise evaluations, and other applications where it is important to characterize the average or equivalent sound level experienced over a certain time period. As you can see in the animation, if you measure sound levels in a busy work area for 8 hours, then you can calculate the time equivalent sound pressure level based on all sources from machine and equipment. And you would get a single value that represents the equivalent sound level over that 8 hours period. Time equivalent sound pressure level is used in situations where sound levels vary over time and help us understand variations in noise exposure. For example, determine the equivalent sound pressure level for the following sources: 85 decibels for 3 hours, 90 decibels for 2 hours, 92 decibels for 2 hours, and 82 decibels for 1 hour. In this case, to hurry up the calculations, we can divide the number of decibels by 10 and move the numbers of hours in front. So then we have 3 times 10 at the power 8.5 space plus 2 times 10 at power 9 plus 2 times 10 at the power 9.2 plus, and we can put it directly 10 at the power 8.2, which gives us the answer. Now we have 10 times logarithm, open parenthesis again, 1 divided by 8, close parenthesis, and it's 8 because it's 8 hours total, times our answer, close parenthesis, approximately 88.95.
All right. So let's go to the next one. And this is an octave band analyzer that measures 80 decibels at 1000 hertz. What be the equivalent for dBA, dBB, and dBc levels? So there are 3 different types of weighting, right? You have dBA and dBB, decibels B, and decibels Cs. And the answer is because all these curves, they meet at 1000, it's 80 decibel for all 3 weighting scales, because there's no difference in a weighting as 1000 hertz, as you can see from the graphic. The sound pressure level measured for A, B, and C weighting scales produce for frequencies higher than 1000 hertz. Usually it's analogous measurements because their differences are insignificant. And this is important because you'll see every time you have a sound measure meter, you have, you can choose between dBA, dBB, and dBc. And you have to know everything that's above 1000, it really doesn't make a big difference. It doesn't make a significant difference. Now let's talk about what happens below 1000 when you have, let's say, the following results for A, B, and C weighting scales. dBA it's 68, dBB it's 81, and dBc it's 90. What is the frequency range for these measurements? It has to be between 10 and 1000 because this is what it makes the difference. And I understand this question, it's very common to most of the CIH exams, this is something that you want to learn, this graph, to understand the differences between weighting scales. And now let's go to the next one. Everybody knows there's a rule of thumb for combining decibel measurements for separate noise sources that are near each other. So, I'll give you an example. Like this is the rule between if the difference between sources it's 0 or 1, you add 3 to the highest. So for example, you have two sources and the two sources are 90 decibels. Then you have 90 decibel plus 90 decibels, the difference is 0. So the correct answer will be 93. But you have to remember, this is a rule of thumb. It's not related to the actual equation. Most of the time you can use it and you can speed up the calculations, and you'll see it's let's say 99.99% it's working. What happens if you add 0 decibels to 0 decibels based on this rule of thumb? If the difference is 0, you should get 3. But again, this is not a law, it's a rule of thumb. Doesn't have to make sense. It makes sense when you add decibels at higher values. So it's good to know the rule of thumb, and you'll see a lot of them in industrial hygiene, but you have to understand this, you cannot apply them all the time. Why do you use the decibel scale? Because it's quite convenient. The sound pressure in Pascal is like from 200 to 0.0000. So we'll just get, fatigued in all these points and numbers and periods. So at this point, we just have to use, the decibel sound scale, which is usually between 0 and 140. And now let's look at the transmission loss formula.
Sound transmission loss is usually a measure of the effectiveness of a building element, such as a floor, ceiling, or a wall, in reducing the transmission of sound from one side to another. Transmission loss describes the sound reduction of a sound striking a surface of a barrier and emanating on the other side. The transmission coefficient for most materials is frequency dependent. That means sound at different frequencies can be transmitted differently through the barrier. As you can see in the animation, a percentage of the sound is reflected depending on the acoustic properties of the surface and the angle at which the sound wave strikes the surface. Some sound wave percentage may be absorbed by the material itself, and some sound percentage is transmitted on the other side of the material. For example, what is the transmission loss for a wall with a sound transmission coefficient of 0.00005 at 1000 Hz. The transmission loss equals 10 times logarithm 1 divided by 0.00005 equals approximately 43 decibels.
So basically, if you know the material, you can actually calculate how the sound is gonna be lost through that material, and they actually use that every time they build a house, and you know, oh, I'm gonna have a drywall. This is the thickness of the drywall. So all this can be calculated. Now let's go to the radiation, and radiation is one of my favorite. I used to work for a CDC, and we did use lasers a lot. And you'll have a question, interesting question about lasers. But let's start with the first formula in the series.
This first equation is known as the inverse square law, which states that the radiation intensity decreases as a function of the second power with distance. This law can be found in various areas of physics. As you can see in the animation, if you double the distance from the source, the radiation intensity is reduced to 1/4 of its original value. If you triple the distance, the intensity becomes 1/9 of the original value, and so on. For example, a radiation dose rate is 100 millirem per hour at 20 feet from the source. What is the radiation intensity at 40 feet or 60 feet? The intensity at 40 feet equals 100 times, open parentheses, 20 divided by 40, close parentheses, square the entire parentheses, which equals 25 millirems per hour, which is actually 1/4 of the original value. For 60 feet, we have 100 times, open parentheses, 20 divided by 60, close parentheses, raised to the power 2, which results in approximately 11.11 millirems per hour.
Okay, so in this case, if you want to hurry up the results, you know, if you are 20 feet from the source, you know, like twice the distance, you just have to basically divide by 4. If you are at 40 feet, you know, just like 3 times the distance, you divide by 9, right? So 4 is 2 at the power 2, right? 9 is 3 at the power at the second power, right? So what is going to be the next one? 4, 9, what's next? You can use your mic or use the chat. Which one you want? 16. Great job, Jessica. All right, let's go to the next one. Oh, this is one of my favorites too.
This equation calculates the amount of radiation that is attenuated as it passes through half layers. As you can see in the animation, a half-value layer is a term used in radiation to describe the thickness of a material that reduces the original intensity of a beam of radiation by half, based on the material's ability to absorb ionizing radiation. This concept is mainly used in radiation protection. For example, a radioactive source emitting 50 millirems per hour is shielded with a lead shield worth of 4 half layers. What is the new emission rate? As you can see in the animation, by simply dividing 50 4 times. 50 divided by 2, it's 25. 25 divided by 2, it's 12.5. 12.5 divided by 2, it's 6.25. And 6.25 divided by 2, it's 3.125.
Okay, quick question. What happens to the energy that's in the half layer right now, in the material of the half layer? Because it half of the value, but the energy has to go somewhere. What's going to happen to the energy that's in that layer? And you can write on the chat or speak which one you like most. It's going to hit those
It
layers.
says
Yes.
heat, yeah.
Yes, hit. And then we're going to have some, what's going to happen? We're going to have some type of radiation. It's called like scattered radiation, right? The radiation is not going to stay there. Eventually, it's going to be sent somewhere else, right? So learn about by sure, like every year they have a question about scattered radiation. All right, let's see the next one. Okay.
This equation is about the effective half-life, which calculates the decreasing rate of radioactivity in the body as a function of the biological half-life and radiological half-life. The biological half-life refers to the time necessary for half of the substance to be eliminated from the body through the natural processes like excretion in urine or feces, as you can see in the animation. The radiological half-life is the time required for the substance to decay or transform in a non-radioactive element, although the substance still remains in the body until it is eliminated. The effective half-life as a whole provides a more comprehensive understanding of the overall elimination process, considering both the biological and radiological aspects, which is useful in nuclear medicine because it allows to assess the time it takes for a radioactive substance to be effectively cleared from the body. For example, the radiological half-life of an element is 16 days, and the biological half-life is 42 days. What is the effective half-life? So to find out the result, we have to divide 1 by 16 plus 1 by 42, and then to find out the result, we do 1 divided by the answer, which equals approximately 11.59 days.
Okay, quick question. Which fruit is the most radioactive? You can write in the chat, or you can say.
They say it's banana.
Yes.
Jessica.
Yes, that's correct.
Okay, thanks, Jessica.
Yeah, because it contains a lot of potassium. So, all right, let's do another one.
As you can see in the animation, in near field power density, the electromagnetic wave is not properly formed because the electric field and the magnetic field are not correctly aligned. So we have to calculate the maximum near field power density using the area of the antenna and the power radiated. For example, Calculate the near field power density for a circular antenna with a diameter of 6 meters, which is a radius of 3 meters, and an input power of 180 watts. In this case, the power density equals, open parentheses, 4 times 180, close parentheses, divided, open parentheses, P times 3 at the power 2, close parentheses, which equals approximately 25.46 watts per square meter.
Okay. I think it was
As you
stopped.
can see in the animation,
Okay, we went through that one. Okay, this is one of my favorite ones. I used it a lot when I was working for CDC, and I think it's one of the most used equations in industrial hygiene that are used sometimes daily by the industrial hygienists.
this equation also calculates the nominal hazard zone distance for a potential eye exposure to a laser with lens. As you can see in the animation, the laser can be concentrated through the lens and become an eye hazard or a skin hazard. For example, what is the nominal hazard zone for a laser beam if the radiant laser power is 2000 watts, the focal length is 30 centimeters, the diameter of the laser beam incident on focusing lens is 2 centimeters, and the exposure limit is 0.2 watts per square centimeter? In this case, the nominal hazard zone equals, open parentheses, 4 times 2000, close parentheses, divided by P times 0.2, close parentheses, raise the answer to the power 0.5, and multiply with 30 divided by 2. The answer is approximately 1693 centimeters, which is 16.93 meters.
I'm just curious, anyone worked in a laser lab? If you worked, let me know in the chat. Because if you work there, you're very familiar of how powerful these lasers are. They actually can cut through wood, they can cut through a metal, they can, if it touches like human tissue, it's a disaster. They're really, really powerful. And what kind of laser, quick question, can, oh, okay, thank you, Kathy. And Lola and Jose. What kind of type of laser can can be used to get somebody blind? The
Class
type of
3B and class 4 lasers.
yeah, that carbon monoxide. Yes, it's the type of lasers that it's actually not allowed to use. I understand even in like war, because it's so cruel. You can get somebody blind from a distance. So that was one of the things that I learned while learning for the CIH exam. It was something that it was like something I did not expect. Yeah. Our laser are general interlocking devices. Yes, of course, that's how they work. Okay, let's go to the next one.
So Daniel, I mean, if it's a total enclosed laser, it'll be still class 1, you know? So you can
Yes.
have a class 4 or class 3B laser, and if it's totally enclosed, and the beam is already enclosed, then it's a class 1 laser. So when you do alignment, that's when there's a potential exposure, you know?
Yes,
I mean,
yes, exactly.
actually, I used to work in a class 4 laser a long time ago, so.
Yeah, I mean, it depends on how you use the device. If there is any kind of potential of concentrating that beam of energy of light in any kind of point, then you know you have on your hands a hazard so powerful that you have to control. And one of the way they control, they use those curtains, you know. But you have to have all the equipment. You have to cover your skin. You have to have the right glasses. The glasses, you know, have to be. You have to match the lasers frequency with the frequency of the glasses. So it's. I know somebody that's a laser expert. It's very complicated. So let's talk about the absolute gain. This will be the last formula, and then I'm going to start taking questions.
This equation is about the antenna absolute gain that converts the gain for an antenna, which is directivity and electrical efficiency, into an absolute gain. As you can see, the gain for an antenna is measured in decibels isotropic, or dBi. And the higher the gain, or the dBi, the more directional is the antenna. The antenna gain changes with angle and frequency. In simple terms, it quantifies how much an antenna enhances the signal strength in a particular direction. That's why we point an antenna to the direction of the receiver. And this is done in comparison with the theoretical isotropic radiator, which is an ideal antenna that sends the signal with the same strength in all directions, which serves as the reference or the standard. For example, what is the absolute gain for an antenna that has a 40 decibel gain? The absolute gain equals 10 at the power, open parentheses, 40 divided by 10, close parentheses, which equals 10,000. The absolute gain is a non-dimensional number.
Now let's do some heat stress problems, okay? And I want you, if you have a calculator, you know, start doing the first calculation, you know, of this course right now. So let's go. What is the bulb globe temp? What is the answer to this heat stress problem? What is the wet bulb globe temperature value for a sunny day if the dry bulb temperature is 90 Fahrenheit, the globe bulb temperature is 105, and just a second, and the natural wet bulb temperature is 85. So get your calculators and do the calculation. I'm just curious who's gonna write in the chat the first result. All right, Lola, that's good. 89.5 Fahrenheit. You are the fastest. Okay. Yeah, it's but you have to do it yourself. That was the whole thing. like try to get the dexterity there. This is one of the things, if you go along my videos, try to beat me. It's very important in the CIH exam, your dexterity, just to go over there and click it um, as fast as you can, or type it into your calculator as fast as you can. So, I mean, we're not, we're just trying to get the dexterity there. All right, let's go to the next one. Can anyone tell me, and you can write on the chat, what's the difference between the previous one and this equation? Night, exactly. You have day and night. And you already, if you know the difference, you already know the difference between these two formulas. And look for these words if there's any heat related problem. Is there day or is there night? Okay, so let's see who's going to write the first exam. I know the answer is 86.50, but I want to check again the dexterity. Who's going to type it and get it on their calculator fastest? Oh, I got a 7.85.
Yeah, 7.85. Yeah.
Okay. Oh, it's no, the first one who can write it on their calculator. You can use your screen calculator, or you can use your hand calculator and then type it. Okay, Kathy and Lola comes actually in the same minute. Oh, that's good. This is basically like I forgot what's the name of that movie that it says with the Karate Kid, right? In, out, in, out. You have to do the problems and get the dexterity there. So, all right, let's do this one. Okay, no cheating. Make sure you do this. I'm gonna read it, and I'm gonna tell you when to start. Okay. So, what is the solution for the following problem, which is for the recommended weight limit? And it's in pounds for a worker is performing the following test with the following factors. Okay, you have a bunch of factors here, but what's important to know that they will give you the factors. You have to put them as fast as you can. So let's see what factors do we have here. We have the frequency factor, coupling factor, distance factor, asymmetric factor, vertical factor, horizontal factor. I forgot what LC stands for. But anyway, are you ready? We're gonna start. 3, 2, 1, go. Good job, Lola. That's what I wanted to see. That's the right number. Yeah, so sometimes, and this happened a lot to me in the past, like, and it still happens, like I hurry up and to put the data, and then I just make a mistake at the end, and that like destroys the whole result. And then it's more complicated for me to go back, you know. So, that's why you have to practice. And yes, yes, Jessica, it's wipe on, wipe off. That's the thing from Karate Kid. Okay, what is little dose? Okay, you probably know if you have experience with um, toxicology, and you're gonna have an entire class on toxicology. A little dose of 100 kills all the exposed animal. Little dose of 0 kills how many? None, exactly. How about how much of the population kills LD 50? 50%?
50%.
Yeah, or half, yeah. So as you see, if the curve is very shallow, then it takes a large dose to kill. If it's very steep, it kills right away. So great job, Jose and Chris. Now let's do another calculation, okay? And don't look at the results, okay? Just try to calculate it yourself. If 50 milligrams of narcotic drug causes 150 grams lab mouse to sleep for 30 minutes, what dose it would take to put a 1.5 kilograms. So remember, you have 150, and now you're trying to put down 1.5 kilograms. How much is 1.5 kilograms in grams? Can anyone tell me how much is 1.5 kilograms? See, I put one dash, one comma kilograms instead of 1,500 exactly.
1,500, they said.
Yeah. So
Yes.
in Europe, we instead of period we use comma. So yeah. So 1,500, and it's you wanna try to put it to sleep for 1 hour. You can start doing the calculations right now. $300. That's correct. Great job, Lola. The first can be done in your head. Yeah. I mean, it's basically 100. That's yeah, that's how it works. So 100, 300. Okay. All right. So that's what I'm trying to say. Like make mistakes now, then make mistakes there when you are there. If you have questions, you can ask me questions now, but you cannot ask me questions during the exam. So, I'm sure you're gonna have questions now, but if you have other questions, reach out to me on LinkedIn, and I'll try to respond as soon as possible. So for this presentation today, I would like to thank first of all Bruce Donato. His emails helped me and helped a lot of my friends because I forward them. He's very helpful together with the team, of course. And my colleague Mike Henderson, Dr. Mike Henderson, who's a CIH, and he's my colleague at Hattie Environmental. He's a great guy. You can find him at the American Industrial Hygienist. It's called Connect now. It used to be called Conference, right? An expo. A question: anyone has a good source for practice problems? Yes, that's. Let me go. This is the one that this again. These are the books that I wrote. You will have a lot of practice problems within these books. The less expensive way to get them are from Amazon. Again, if you want the CIH exam practice audiobook, I have 25 free codes. Write to me on LinkedIn on Dr. Daniel Farkas, and I'll send you the code. That code is only gonna work once. Once you use it, it cannot be reused. So it's personalized. It's a bunch of letters and numbers there. But this is how much the publisher gave me. So I only have 25. And I remember the first time I only asked for 25 because the first time we only have like 20 students when I talked to you, Tim, right? That's how many we had. So I was like, 25, it's more than
Right.
enough. But this is great turnout. And if you want to see the animations, like all of them, these are the videos, and you'll hear my voice for hours and see animations for hours. So, and thanks God for Cat Candy CIH that helped me with that. So we still have about 10 minutes. I know we're supposed to take every 10 minutes every hour, but always this last 10 minutes for questions. So please ask me any questions. You can write them in the chat, or you can Jessica, yes, I have the audiobook. The audiobook is my current commute and listen. Yeah, that's the good part, audiobooks, because I don't read books. I haven't read books in like 10 years, but I have listened to a lot of audiobooks, and a lot of people told me like, I got the audiobook and I listened to the audiobook, and at the time that I'm taking the exam, I just remember phrases from the audiobook. And it's you basically, if you listen to it, and it's 6 hours and a half, and everything is concentrated there. And I basically try to put everything you need just to pass the exam, but nothing more that will be unnecessary. So I got you basically everything you need, just enough to pass the exam, but not too much to fill your head with unimportant stuff that you can learn later on, you know. And I think this is one of the problems that you see in the books today. It's a chapter this big, and the information that you need, it's actually this much, So try to keep it straight to the point. Thank you, Tim, for your like. We're gonna have another session. I think it's in 4 weeks. It's gonna be after the spring break. So we're gonna have. Let me give you. I'll give you the site. Just a second. Where you can go and you can see all the books. This is the site. Okay, yes, April 18. So if you have questions, you can save them and ask me then. We're gonna have another. Okay. Thanks again, Jessica. If you can also review it, that's good, because the more reviews I get, the more free stuff I get from the publisher to give for free. Yeah. So any questions? We have 7 minutes.
I mean, I just want to thank you. I mean, your graphics are really great. I mean,
Thank you. Yeah,
very easy to understand it when you have that spectacular graphics in your lectures. That's really good.
yeah, no, I have to thank my colleagues and at West Virginia University. They taught me how to do graphics, and CDC, Center of Disease Control and Prevention when I was there. and Hattie Environmental, and in Bowen Environmental Health and Safety. I did a lot of presentation for them. If you go on their website and you put my name, you'll see all the presentation. I did a presentation last month actually about and this is a great job to have if you are an industrial hygienist. Try to get a job as a safety professional on a movie site, like where they make movies. Um, so if you're on a movie set, you're gonna have a lot of good experiences. Um, you know, um, you probably seen uh, in the news these days that there were like some accidents with firearms. But as an industrial hygienist or safety professional, you're not going to handle firearms. You're gonna handle basically a lot of other stuff. But they have what call like an armory officer, somebody that is actually licensed or certified. And I had no idea that safety professionals are wanted on a movie set. And when I got the first job, I was amazed, you know. And they make you sign this non-disclosure contract, you know. And I signed a non-disclosure contract, and they say like if you sign it, um, and you talk about what you've seen on the movie site before the movie is released, they're gonna have a problem with you. After the movie is released, there's no problem. But I think it's a great experience, and every safety professional should have it to go on a movie site and see these like superstars, that you see them in the movie sitting next to you and actually listening to you because they're concerned, they have safety concerns. And like if you're a safety professional on a movie set, everybody's going to listen to you. Like if you go on a construction site, people are going to look at their phone, and it's like you have to say put your phone down, but you get more respect on a movie site. And I think that's a great experience. If you ever get the gig to go to California, do it. That's my advice. It's an aspect of industrial hygiene that I never experienced before, but it's very interesting. Any questions about the exam? I think everybody's tired after 3 hours.
Just want to say it's a great talk. I really enjoyed it. I mean,
No,
I
thank
started
you.
my day like 6:30 in the morning today. So it
Yeah.
was still, I mean, your lecture was very stimulating.
Yes,
Just
thank you.
wanted to mention
And
that.
thank you, Sarat, and thank
Oh,
you,
you're
team.
welcome anytime,
Yeah, and Bruce, because the number of CIHs are declining, right? That's what I heard. There were like 6,000, we're going down to 5,000 right now. So we need more CIHs,
I
as
think
you
a lot of
said.
them are retiring.
Yeah, exactly. A lot of them are retiring, so we actually need, and this is a difficult exam. There are about I think 60,000 CSPs, but only 5,000 CIHs right now. And there's about 1,000. My wife is studying for the DABT, which is the toxicology exam. It's like about 1,000 of toxicology board certified people. We need to get those numbers up because this is the industry. If we don't have the right safety professionals in our industries, then they're just gonna move the factory somewhere else. So we have to make sure that we protect the workers here, so we won't have any, workers' compensation cases and everything that's going up next. So yeah, that's I'm trying to help any CIH student, like even if you send me a question, I'm not let's say it's the weekend, it's uh, on Friday evening, you ask me the question, I'm going somewhere I'll respond by Sunday evening or by Monday evening if it's like the long weekend. So I'm trying, like to get more people to join the CIH profession. So it's 9 o'clock. Do you wanna have some closing remarks?
Yeah. Hey, Daniel, you're getting a lot of love. The emoji clapping hands.
Thank you.
You did a phenomenal job. Surat, same thing.
Well, thank
You
you.
guys did a great job. You did a great job facilitating. You all just received an email with the link to the Google Drive where we're keeping all the files. So yeah, the presentation from tonight will be there. I'll probably do my session later on that I didn't get to this evening, or maybe before. We'll have to coordinate it, like everyone come on like a half hour early, one of these sessions. But yeah, so I think it
Thank
went
you so
very
much.
well. Yep. Thanks for all the great questions and interaction. We're off to a good start. So thank you all for being here, and we'll see you Thursday night.
I do
Okay.
have a question. It says I cannot
Okay.
open the link.
It says what? I
Uh,
cannot open the link.
Yeah.
If you can't open the link I just sent, then send me an email and we'll have to figure it out. If you have an
Okay,
alternate
thanks.
email, that seemed to work for somebody that couldn't get the textbook downloaded. They used an alternate email and that seemed to do the job, but we'll have to troubleshoot that. So let me know right away if you can't get to the folder and the files that we just sent you, where all the course materials will be stored.
yes,
So
and I'll come to the next presentations. I think the only exception is the week after next week because it's spring break and I'm going with the kids in a trip. But I'll come to each other presentation and if I have some suggestion or some commentary, I'll write in the chat or I'll let the presenter know.
okay, that'd be great, Daniel. And we're extending the offer. We're not committing you, but if instructors can come on to the next session a half hour early to answer some questions, then we'll try to do that as much as we can. But we're asking a lot out of these instructors. They're volunteers, but if you can get on early, a half hour, Daniel, next session, that's great. If not, we certainly understand. I'll try to answer any questions to the best of my ability, but I'm no Danielle Farkas, so but
Oh
uh,
no, everybody's himself, that's the best way. That's how it works the
yeah,
best. So
Sirach can help us out too.
yeah,
I'm sure he's more than capable.
No, I mean, I'm just the experience. I mean, you guys are way smarter than me. So,
So on the course schedule, there's a column that says recording. If it's a Y, that means the instructor said yes, you can have it recorded. If it's a no, there'll be an N. One of them or two of them have a question mark. We haven't heard back from the instructor if they're going to allow us to be recorded, but I think there's only one or two with the question mark. We'll try to get that squared away, one way or another, as soon as we can. But as the schedule changes and the instructor bows out for some reason, I'll continually send the updated course schedule, but look for updates on that recording column. Most of them are filled out, so we know which ones are not going to be recorded, and that's just a few. So that's how you know which classes will be recorded, and so you want to try not to miss those. The headings on the file I have is missing. The
that's
headings on the
just reading here.
Yeah, get with me later, Jessica. We'll find out what's going on there. But one thing I shared is the equation sheet that I doctored up with Photoshop. I put the variables, a name for all the variables, and the units, and the just the name for the equation. It kind of helped me. So what I did is I put it in a protector sheet, the doctored, the Photoshop version. It's not coming through. Sorry about that. And
No,
then
it's
on the
not coming
back is
through.
the actual equation sheet from ABIH. It's not coming through too clear. But just like a giant flashcard with the doctored up Photoshop version with the name of the equation, the units, and I just as I did practice problems as I studied more and more, I got familiar with the equations so that when I saw the naked equations that you'll get on the actual exam, I know exactly, oh, I know what that equation's for. I know what it's called. I know what V stands for. I know what VP stands for. I know the units that we're supposed to be using. So uh, those will be in your bonus materials. I just gave you sort of a sneak peek for one of the sheets. But the caveat that was from 2011. So it's up to you to if you want to see if there's any difference between the one they give out now and the one that I doctored up. That's on you to figure that out.
Tim, I have a question. It says class schedule is for 2015.
Yeah, I thought I fixed that. The header should say 2024,
Okay.
but we'll fix that. That is the current course schedule.
So I just wanted to mention one thing about the equation sheet. It is embedded in your exam. There's no paper copies that are given to you, nothing like that. So just wanted to mention that.
When you use the background filter, it blurs. Oh, thank you. See, I learned something. I don't think I'll be able to figure it out here. Let's see, go to view. I think that's in settings, right?
I think it's stop video, where you go to stop video, and then it says choose virtual background. See, you have stop video, and there's a sign there next to it.
Okay,
And
yeah,
you
there you
click
go.
it. Yeah, okay.
I don't know how close up you can see that, but anyway, it's one of the files
It's
that I
great work,
uploaded.
by the way. I know how difficult it is to do that. You
Yeah, I
have to
probably
fit
spent
everything in there.
way too much time on this with Photoshop, but it was a way to get familiar with all the equations. That's for
Tim, do you
sure.
want me to stop recording now or do you want me to go ahead?
I think we're done. Yeah.
Okay.
One
Good
more
job.
thing, I just
Oh.
remember something. If you are coming to the American Industrial Hygienist Conference, I'm gonna have free paper books there. So stop by the Hetty booth, and I'll get you a free paper book. Oh, you have the book yet? Yes.
Very cool.
Great job, thank you. So, yeah, that's all. Have a good night, and
Okay, thank
keep
you.
keep on.
Thanks, Daniel.
Oh,
Thanks
thank
again,
you,
Daniel.
Laura.
Good work.
Danielle, thanks again. Great
Thank
job.
you.
Thanks, Sarat.
Thanks, guys. Thanks for coming in. Thank you.
Good night, everyone.
Good night.
See you Thursday.